So let's correct this one. Let's apply BPLV to calculate this series. So what we want to apply it for, we would like to apply it to say that the sum of the integral is equal to the integral of the sum. Okay, so one way to do this and then determine this limit. So we could do it in either way, but I think let's try to calculate the sum of x to n, keeping in mind that x is between 0 and 1. That should remind you of something. That's the sum from 0 to infinity of x squared to the n, so you can identify geometric series. If that's now giving you some ideas, it's still time to pause the video and try to solve the rest of the exercise. Well, otherwise, let's see that. So the sum of the squares of x to the square to the power n, what is that equal to? So the geometric series, that's 1 over 1 minus x squared. If x is in absolute value, strictly smaller than 1. So for us, what do we have? We have that the sum of x to the n for x between 0 and 1 is going to go to 1 over 1 minus x to the square if absolute value of x is strictly equal smaller than 1, and if x is equal to 1, because it's inside of the closed interval 0, 1, if x is equal to 1, then the sum of x to n, that's the sum of ones infinitely, that's equal to plus infinity. However, you see that the value that is problematic, well, maybe let's try to represent the limit function. The limit function to this series is going to be, well, 0 outside of 0, 1. And otherwise, it's going to be 1 over 1 minus x. Sorry, it's going to go to be 1 over 1 minus x. Something like this. Okay, so that's so that it has some asymptote here, some vertical asymptote here. So the 1 over 1 minus x is going to be something like this. Okay, and so and the value at 1 is going to be plus infinity. Okay, so what do we have? That's kind of a trap, actually. All right. What do we have? We have that the series inside is going to go to 1 over 1 minus x, so that the series of the integral, that whole thing, is going to converge to, as n tends to infinity, well, as the series goes to infinity, it's going to be equal to the integral of the sum, which is 1 over 1 minus x between 0 and 1. And if you remember your improper integrals, that's the diverging one. Well, even if you don't remember improper integrals, that's going to be the log of minus log of 1 minus x, and so that's going to be minus ln of 1 minus x between 0 and 1, and you know that this is equal to infinity. Okay. All right, so what we have, that this is equal to plus infinity, and we could say that because of this. But we could also have a convergent series, and in the case of a converging series, then we would have that it's equal to the integral of the sum. Okay, it's they will have the same nature. All right, and to correct the one for the decreasing sequence, so let's see. First of all, we need to know whether it is indeed pointwise increasing, pointwise decreasing or increasing. So let's consider x over n. So that's the n, that's the x on the top. As n tends to infinity, that goes to 0. So that sinus of x over n, as n tends to infinity, that tends to sinus of 0. So sinus of 0 is equal to 0, all right? and so that we have that the limit of this sinus of x over n times 1, 0, 1 x is going to be the zero function for all x between 0 and 1. And first of all, that's one thing. So the pointwise limit is the same everywhere. It's going just to be the zero function. That's one thing. And the second thing is that increasing or decreasing? For x over n, if I want to compare x over n to x over n plus 1 for positive x, of course, this is going to be bigger, x over n, and sinus is itself between, so that's sinus of x between 0 and 1. It's an increasing one, so that the sinus of x over n is greater than the sinus of x over n plus 1, so that as a sequence, pointwise, this is decreasing. Pointwise, we've got that f n plus 1 of x is smaller than f n of x for all x between 0 and 1. All right? So that it's converging almost everywhere, well, actually everywhere, to the zero function. It's a decreasing, pointwise decreasing sequence. Furthermore, we needed one more hypothesis that f1 is bounded. What is f of 1? f1 here is f1 of x is just sinus x times 1, 0, 1. So of course this integral is bounded. It's even equal to the cosine 1 minus the cosine of 1. So that's no problem for that. And what else? And that's all. And that's all. We've got all the hypotheses. Integral of f1 is bounded. F is integrable. Yes, of course, that's one of the conclusions. It's pointwise decreasing. It converges almost everywhere to some specific function. So we've got that the limit of the integral of the sequence is equal to the integral of the limit. So that's equal to the integral of the zero function, which is equal to 0. Okay, so this is it for this exercise. So you can try to apply these to some exercises in the worksheet and the corresponding worksheet now. See you very soon.